Let us now talk about this problem. We are given an array. For every element, we need to find ceiling for this element on left side. Let's understand the problem with this example. For first element, there is nothing on the left side, so we print -1. For second element, there is no ceiling on left side. So when we say ceiling, we mean smallest element which is greater or equal to the given element. So we have only one element on left of 8 which is smaller. So we are looking for elements which are equal or greater. So we print -1. For 30 we again have both the elements smaller, so we print -1. For 15 there is only one element which is greater, so we print that element as output of ceiling. For 25 there is one element which is greater, so we print 30. For 12 we have three elements which are greater or equal, 30, 15 and 25. Out of these three elements we need to print the smallest one, so our output is 15. When you have an array sorted in decreasing order, your output is going to be -1 for the first element, and for remaining elements just going to be the previous element, right? For 20 it's 30, for 10 it's 20. Suppose there was one more element 5, the output for that would have been 10. When you have an array in increasing order, your output is going to be -1 because you never have an element on left side which is greater or equal. Let's see this example. For 6 it's -1, for 18 it's -1 because there is nothing on left of 6 and there is only one element of 18 on left of 18 which is smaller. For 4 there are two elements which are greater here, so output is 6, smallest of these two. For 5 there are two elements on left which are greater. Out of these two, 6 is the smallest. Now please pause this video and try to think of an approach that works in big O of n log n time. Your approach may use big O of n extra space. Let us talk about naive solution to solve this problem. So for first element, it's always -1. So we print -1 for the first element. We now traverse remaining elements starting from the second element. And for every element, we go to left of it. And every left element is compared with the current element, and we see which left elements are greater or equal. Out of these left elements, which we see which has the minimum difference, right? And we store this minimum difference. We initialize this minimum difference as positive infinite. So the code that I have written here, it is some language independent code. In C++, you can have positive infinite as int max. In Java, you can have it as integer.maxValue. This print is cout in C++ and system.out.print in Java. So we go to left of every element, we find the minimum difference, and if minimum difference remains positive infinite, then we print -1 for this element, which means there was no element which was greater than this element or equal to this element. If we do not have it as positive infinite, then we print the ceiling as array I plus diff, right, which is array j, the j for which was the closest one. What is the time complexity of the solution? This is clearly a big O of n square solution. There are two nested loops. So the time complexity of the solution is big O of n square. And it requires big O of 1 auxiliary space. Now again pause this video and try to think of a solution which is n log n. An efficient solution to solve this problem is to use cell balancing binary search tree. In cell balancing binary search tree, we can do insert in log n time. We can find the ceiling also in log n time. So the idea is we create an empty cell balancing BST, and this cell balancing BST is represented as set in C++. So there is a container in C++ which represents cell balancing BST called set. Map also represents cell balancing BST, but the difference between set and map is set is for single elements and map is for key value pairs. Tree set in Java also implements cell balancing BST. Both of them implement red brick tree. So before we create a cell balancing BST, we have printed the output for first element as -1. We all know that for first element, ceiling is -1. Once we create cell balancing BST, we insert the first element into the cell balancing BST. So our cell balancing BST contains 2 only at this point. Now we traverse through the remaining elements, and for every element, we simply find ceiling of this element in the cell balancing BST, which is a log n operation, right? If there are n elements in the cell balancing BST. If we find a ceiling, then we print the ceiling. If we do not find the ceiling, then we print -1. And after doing this if else, we insert current element into the cell balancing BST S. So that's the simple idea. The function to find ceiling in C++ is lower bound. If there is a ceiling, it will return the ceiling, iterator to the ceiling. If there is no ceiling, then it will return iterator to the end, which is a special iterator in C++ that indicates not present. In Java, there is a function called ceiling in tree set, which will give you the ceiling if it is present. Otherwise, it will give you null. So we have functions available and we can implement this code either in C++ and Java. And the idea is simple. We use this property of cell balancing BST that we can maintain a running set of sorted elements. Let us quickly analyze the time complexity. We are running through n elements. We are finding the ceiling, which is a log n operation. We are inserting the element, which is also a log n operation. So the time complexity is n log n. You can try other data structures. If you try to use hashing here, you will get higher time complexity because you can't find ceiling efficiently from a hash set in Java or unordered set in C++. You can notice this thing in library documentations. If you see the tree set documentation, there's a function called ceiling. It's not there in the hash set. If you see the library documentation of set, there's a function called lower bound. It's not there in the unordered set.